Oh, hello. One of the things I like about this country is that practically nothing ever changes. This is the Times for Thursday, July the 2nd, but 1908. And I look on page 6, and it's talking about the speed of motor vehicles. And then just below that, London street traffic. So what, I ask myself, is new? Now, when I have a paper, usually the first thing I do is turn almost immediately to the letters page. I don't know why. I suppose it's one of those things. And by and large, as a scientist, I would not expect to see anything of great interest very occasionally. But if I'd been reading this paper back in 1908, I think this thing would have certainly caught my eye. It's a letter from a lady in Godmanchester, and she writes as follows. Sir, I should be interested in hearing whether others of your readers observed the strange light in the sky, which was seen here last night by my sister and myself. It was in the northeast and of a bright flame colour like the sunrise or sunset. The sky for some distance above the light, which appeared to be on the horizon, was blue as in daytime, with bands of light cloud of pinkish colour floating across it at intervals. An hour later, at about 1:30 in the morning, the room was quite light, as if it had been day. Now, the first thing I want to emphasize then is that very occasionally, even in something like the Times or other papers, there's a piece of information which we can use as data. And part of what the scientist is, he's many things, and she is many things, of course, is a detective. We're trying to build up clues. And no doubt, nearly everybody who read this just put it away and said, oh, that's all very interesting, and so forth. However, something else was also happening on that day, and also in this country. What was happening was, in fact, this is a record from a weather station. It's in Cambridge, in fact. And what we're looking at here is the fluctuations in the air pressure. This is the thing which we call the product of a microbarograph. And this ink line here is tracing out as the hours and minutes tick past. Now, as you can see, there's nothing terribly exciting. It rises very slightly there, then dips down, and then continues. And then suddenly we come across these tiny squiggles. The investigator realized straight away that there was something which was worth looking at. He wrote, "Not artificial." Now, what I've done is actually have this little bit enlarged so that we can see it more clearly, and it begins to reveal something quite remarkable. Here again is our air pressure, and notice now that we are in fact at 5 o'clock in the morning. That's about 4 hours after the lady who wrote to the Times had seen that bright light in the sky. And at about 5:15, just here, do you see suddenly the air pressure goes whoops down like that, straight back up again, and da-doing, 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 da-doing like that. And at 25 minutes past 5, there's another mass of very rapid oscillations like that before it eventually dies down. Well, what on earth is going on here? There are two strange things which are reported in England. Now, I think the way to think into this is to imagine that you're back in a thunderstorm. I'm sure you're all familiar with this. The thunder's rumbling around. Suddenly there's a flash, and then the thunder rumbles through. And of course the reason for that is that the lightning has an almost instantaneous time to get to you. It gets there immediately. Very, very fast indeed. Whereas of course the sound travels much more slowly. Now if you then think about it, we've got a bright light in the sky, but the sound has taken 4 hours to get there, which means it's an enormous distance away. But even so, the sound has reached England. So originally that sound must have been absolutely colossal. So what on earth is going on? Well, in fact, what had happened is that in Siberia, and in particular in one area, there had been something, and already reports were beginning to filter out about what had happened. Now, this man here is a chap called Semenov, and later he was interviewed and he gave an account of what happened on that same day. And this is what he wrote. The sky was split in two, and high above the forest, the whole northern part of the sky appeared to be covered with fire. At that moment I felt a great heat, as if my shirt had caught fire. This heat came from the north side. I wanted to pull off my shirt and throw it away. But at that moment there was a bang in the sky and a mighty crash was heard. I was thrown on the ground. For a moment I lost consciousness. This is sounding pretty bad. The earth trembled, and when I lay on the ground I covered my head because I was afraid that stones might hit it. At that moment, when the sky opened, a hot wind as from a cannon blew past the huts from the north. And so he continues. Something obviously dramatic had happened extremely close to him. Well, rather curiously, in some ways, it was a number of years before expeditions were mounted by what was then the Soviet Union in the 1920s to investigate these strange happenings. And here we have one of the pictures from that expedition. There's a canoe being pushed along a little creek. Now, I must explain, this is a very trackless area. There are no roads. You don't just drive there or anything like this. They climbed up a low ridge of hills, and there in front of them they saw something which I don't honestly think they could have believed their eyes, because what happened was, and here we have some of the original footage. This explains why it's so grainy. Those trees have been smashed down over thousands of square kilometers. They have been completely devastated. Clearly something extraordinary had happened in that particular area. This is known as the Tunguska event. Now, the Tunguska event, which happened in 1908 in Siberia, has fascinated people for years. Why is that? Well, quite simply because when the scientists went there, of course they said, well, we'd better find out what caused this thing. So they dug trenches, they sieved the soil, they looked on the ground, and they could find absolutely nothing, nothing at all. It was extremely mysterious. The Russian scientists were speculating, they had the idea that maybe an alien spacecraft, nuclear powered, sounds a little ridiculous, but perhaps it's not, went out of control and exploded. And we can test that idea because we would find radioactivity. And they looked for the radioactivity and it wasn't there. So this has been a mystery which has really been with us for years and years and years. It's always been niggling with people. We had the evidence from England, we have the eyewitness account, and then the expedition went there. What on earth happened? Well, in point of fact, what it was in one of these things. This here is a meteorite. Simple. But where was the meteorite itself? What has evidently happened is that this meteorite, which was much, much bigger than this one, it was roughly the size of the Albert Hall, which is big, but not as big as you might think, came into the Earth's atmosphere and it exploded completely at a high altitude, so that only the tiniest fragments remained. And very cleverly, they have now been found. Now, I want you to imagine that this piece of wood here is from the forest in Tunguska. And I think you can see quite clearly the growth rings like this. Well, let us say that this growth ring here represents 1908. Well, as you saw in that footage of the film, nearly all the trees were knocked over. They died, of course, but a few did survive. And then, afterwards, they carried on growing until the day, of course, the tree was cut down. Well, if we go back to that 1908 growth ring, an Italian group of scientists have looked extremely closely, and they have, it appears, recovered tiny particulate pieces of material which are derived from that meteorite. So we've clinched that argument. But it again shows you we're dealing all the time with clues. You might even have to look for evidence inside a tree trunk before you actually find what you're looking for. Well, fine, that might be that. A huge rock, relatively, falls out of the sky in 1908, and the Times readers learn about it. It appears that perhaps nobody was killed, maybe one or two, thank goodness for that. But it's in the past. Not many of us have been to Siberia, so why should we worry? Does it really matter? I think it does, and I'll tell you why. What I want you to imagine is that we're going to look at the globe here, and here is the actual impact site, all right, of Tunguska in Siberia. Now, just supposing back then in 1908, the meteorite had arrived slightly later, a few hours later. What would have happened? Well, of course, the Earth would have rotated, and this time, now what's happening, I suggest, is that the target has been subtly shifted. The target is now the Royal Institution in London. Well, what would actually happen? I think this is rather sobering. Here is a map of London, and to help the orientation, we've put in part of the M25, which is the outer ring, the red ring there. That's really enclosing the best part of London. Now, what we're going to do is look at the footprint of destruction as measured by the scientists in Siberia, and we're going to transfer it onto London. What do we see? That inner zone, which is a red oval, is what we call the fire zone. In other words, this in Tunguska was where all the trees caught alight and nearly everything was destroyed. This is a sort of reconstruction of what might happen in London was a similar sized object to explode above our city here. Well, of course, that's just the inner zone of destruction. When the scientists were looking around Tunguska, there was an outer zone of destruction, which is now shown here in this larger area, which, as you can see, more or less falls within the M25. Now, this is a zone of very severe structural damage. There will probably be some damage, even as far away perhaps as York and Swansea, and the sound of this impact would be heard across a good part of Europe. Though we should always remember that there's nothing special about giant meteorites hitting Siberia. They can land anywhere on the Earth. Let's continue the game of allowing a few more hours to elapse, and we're going to rotate the globe a bit more. And this time the impact site is above the Atlantic Ocean. Perfectly safe. There's nothing to worry about. It's way away. Or is it? Well, what we have here is the Atlantic Ocean in miniature. I should explain that one of the things scientists very much enjoy doing is building models to constrain their calculations. And because it would not be practical for us to bring the Atlantic Ocean into this lecture theatre, what we have done is built something which approximates it. And I should explain, because there are a few details here which will be quite important, I think. Here we have a city on the coast. It could be Liverpool, or it might be on the other side of the Atlantic. It might be Manhattan in New York, for example. You have the coastline, and then this sloping ramp down here represents what we call the continental shelf. That's underneath the water, but is going off into the deeper water. And then we have the Atlantic Ocean out there, but the blue material down at the bottom is our Atlantic itself, and above it there is another liquid. And I'm sure all of you are saying, what earth is going here? We all know about the Atlantic Ocean. It doesn't have another liquid above it. Well, it doesn't have another liquid above it. What it does have, of course, is a fluid, which we call air. What I'm going to do is pour this fluid into here, which you can see has been kept back by a special gate. As I pour this fluid in, of course, it's higher than the surrounding liquid, and it is, in a sense, storing up the energy. This is what we often refer to as the potential energy. And when I lift this lock gate in just a moment, that will be the same as a meteorite impact, because all this potential energy is going to be translated into what we call kinetic energy. So here's go. Let's see what happens. Right, a wave is rushing off like that, and it's coming up towards perhaps Liverpool, and it's steepening up, and things aren't looking too good at all. Right. Now that happened very quickly, and what I would very much like to do is if all of us could look again at that in slow motion. Up goes the lock gate. Do you see the wave travelling along? Now, as the energy is being compressed, as it climbs up the continental shelf, a huge wave then begins to break, reach the coastline, and that is what happens when a large meteorite explodes above one of our oceans. Well, meteorites do arrive on this planet, but we don't usually see much evidence for them. Whereas in contrast, if we look at some of the planets up in the night sky, and even our daughter satellite, the Moon, one can see it is pockmarked by various sorts of craters of different sizes, some old, some very new. It's riddled with impacts. The Earth, in contrast, does not show that sort of cratering. Why is that? The Earth is an alive planet, in a sense. It's got an atmosphere, weathering, and plate tectonics all help to remove that evidence of the cratering. So craters on the Earth's surface generally are removed from human sight, at any rate, rather easily. They can indeed be very difficult to find unless you know exactly what it is you're looking for. Now, the other crucial difference in many ways between the Earth and the Moon is, of course, that the Earth is alive, literally, because it has life on it. The Moon is as dead as a dodo. It's absolutely sterile as far as we know. One of the most curious facts, I think, about what we call the fossil record is that nearly all the fossil species are now extinct. Now, I can show you a couple of examples. Here is a fossil fern. This is about 300 million years old. This is a fossil plant, in other words, completely extinct, disappeared entirely. We don't know why it went extinct, or do we? That's one example. Here is another example, rather different. This is the foot of a giant bird, which you can imagine how high it was originally. But this bird probably only went extinct about 1,000 years ago, thereabouts. This is the giant moa from New Zealand. So we have an immediate problem. We have to explain these particular extinctions, and we are going to look for mechanisms. Now, one way which scientists do like to think, in particular, all the time gathering these clues together, is not to say, well, why did the plant and this giant bird go extinct? You can certainly ask that question, but you want to concentrate on particular groups. Maybe they're going to be especially informative. Concentrate on one thing, the answer may become clearer. And it happens that, in particular, there is one very famous extinct group, the dinosaurs, which have vanished from the face of the Earth. And they, as I have mentioned, intrigue us in all sorts of ways. They're fascinating. This is one sort of claw, not quite a toenail, but a giant, sort of, it's the equivalent of that little thing there, which belongs to a dinosaur which was actually collected in Sussex. It was probably a fish eater, and that's just one part of a huge animal. And if you are into large animals which are dangerous, and the fossil record's full of them, then here's another very famous example. This is the one tooth of the Tyrannosaurus rex, the huge carnivore. So those dinosaurs have disappeared from the face of the Earth. Now, dinosaurs are by no means restricted to Sussex and such places. You can go and collect them in all sorts of fascinating places, such as Mongolia and the United States and South America. And they were worldwide in distribution. But one thing which I think is very important to mention is that dinosaurs can be found in this country, England. And here is a fossil dinosaur from the Isle of Wight. It's actually a piece of backbone, as it so happens. And you can go and find pieces of such dinosaur bone with no problem at all. Now, here is part of the coastline of the Isle of Wight, and we can see a cliff, and exposed within it is a whole set of sediments. If you know the right places to look in the Isle of Wight, you can find bits of dinosaur really very easily. They are common. You won't find whole skeletons as a rule. That's the luck of the draw, but you will certainly find them. But if you go to the sediments which are younger than 65 million years, you will never find a dinosaur at all. I mean, this is a fact observable which you can employ yourself if you are collecting the fossils. They have vanished completely. They are entirely extinct. Now, when we think about the disappearance of the dinosaurs in various ways, it's understandable one's going to concentrate on ideas which relate specifically to the dinosaurs. And as you might imagine, there are no shortage of those ideas. There are lots and lots. Here's just a couple. Now, this thing here looks a little bit like a human skull, but it's not. This is a dinosaur egg. At the same time as the dinosaurs were flourishing, there were many other animals, which included the mammals. Now, the mammals were literally overshadowed by the dinosaurs. The dinosaurs were gigantic, the mammals were tiny, but those tiny mammals had sharp little teeth, and many of them enjoyed eating eggs. And it has been seriously suggested, and it's not a foolish idea, that the nibbling away of eggs by the mammals led eventually to the disappearance of the dinosaurs. They just couldn't keep up with the level of egg eating, so to speak. The problem with that idea is that mammals and dinosaurs have been coexisting for a very long time indeed. Some of the other ideas are really faintly ludicrous, perhaps. It is known that sometime before the dinosaurs left us, the vegetation on the planet changed in rather dramatic ways. And it has been seriously suggested that with the change in the vegetation, the digestion of the dinosaurs was so upset that they suffered from truly massive constipation. And so when you see something like this, fossil feces, the thought of suffering from 40 million years constipation doesn't really bear contemplation. But it was an idea which was suggested, and maybe there's just a tiny kernel of truth somewhere in that. What really matters is that at this time, 65 million years ago, this is an interval which we call the Cretaceous. It wasn't only the dinosaurs which went extinct. And so it's no good appealing to egg-nibbling mammals or constipation. We've got to look wider. Now, the sorts of things which went extinct are such things as this really lovely reptile jaw. This belongs to a marine reptile, not very closely related to the dinosaurs, still a reptile, and you can see the upper and the lower jaw and those ferocious array of teeth. We do know, in fact, sometimes what that sort of reptile hunted. It hunted, amongst other things, these beautiful little ammonites. They are extinct. They went extinct at the same time as the dinosaurs. And who else joined them at that time? Well, they include such things as this rather remarkable object. This is a belemnite. Now, belemnites are a sort of fossil squid. This is the internal skeleton which the animal secreted for itself. And they can be quite abundantly found as fossils, but you'll never find one in sediments which are younger than about 65 million years. So, quite clearly, if we're going to look for an extinction event which involves not only the dinosaurs, but the marine reptiles and also the flying reptiles and the ammonites and the belemnites, we've got to look for some sort of more general explanation. And the story, in fact, goes to a group of people which were led by two very remarkable scientists. This is Luis Alvarez and his son Walter Alvarez. Luis Alvarez is a very distinguished physicist. He's died now, and his son Walter is also a very distinguished geologist. They wanted to discover what the infall of meteoritic material might have been. Now, when we talk about the influx of meteoritic material, we're not, for the most part, talking about these sort of giant things here. They do occur, and as we've seen already, sometimes with catastrophic consequences. But nearly everything which actually falls to the ground are these minute little things here. These are little things called micrometeorites. They're incredibly small. If you're collecting samples through the rocks at regular intervals, the last thing you want to do is to break down a whole lot of rock and then painstakingly go through them looking for those tiny micrometeorites. How incredibly dull. Scientists love shortcuts, and there's a clever one which we can use here. And it depends crucially on this element here, which is known as iridium. Now, the point about iridium is that if you try and measure it out in the crust of the Earth, you will need the most sensitive machines on Earth to find it. It is fantastically uncommon. And that explains why this small heap of iridium here in my hand is worth a small fortune. It's not easy to get hold of. There is, however, something very curious about iridium, though, because although it's very rare in the crust of the Earth, it's actually surprisingly abundant in many sorts of meteorites, big ones here, and in the micrometeorites there. So all you've got to do is to measure the concentration of this iridium, and if their hypothesis was right, then there would be some slight changes, maybe suggesting more micrometeorites were falling in. Because you see, at the moment, the general calculations suggest about 100 tons a day arrives on the Earth, which is quite a lot. Well, let's see what they actually found. Here we have what we call a stratigraphic column. This is just the rocks piled up one above the other. And here we are measuring the amount of iridium. And, of course, there are very minor fluctuations as we continue upwards here. And that's what we'd expect. But this bar here, in fact, represents extremely low concentrations. And then we find what happened with the Alvarez team, because suddenly there is this most colossal spike of this element iridium, which coincides rather precisely with a rather special and identifiable bed. So what we're really beginning to think about is there some possibility that there was some event, if you like, something which was leading up, not to the infall of something which is just a few extra grains of this, or even something of this particular size, but one is marching towards something where one is dealing with an absolutely sort of catastrophic and in many ways unbelievably violent event. Good Lord. Yeah, well, Quite so. Dear, dear. On the basis of a single spike of iridium, Alvarez, father and son, suggested that the only way that could be interpreted was some huge rock falling on the Earth 65 million years ago, rich in iridium, which was then spread around the place. This is effectively an asteroid impact, and if you are living just there, it's very bad news indeed. But I'll show you in a moment, it might be worse than that. Well, again, what I always want to try and persuade you is that the scientific method is something which is open to testing, and it is always possible to make mistakes. Could they have been mistaken? That's a very dramatic hypothesis on the basis of single chemical measurements. Well, this here is in fact a piece of the boundary clay. It's one I collected myself, as it so happens, and when I collected it, it was actually that way up. And what we have here is that the iridium anomaly is found in this so-called boundary clay. This is a critical division because underneath it there are sediments in which you might find dinosaurs. And above it, you will never ever find a dinosaur. This is the event 65 million years ago. Well, there are other things in this so-called boundary clay, and in particular, in many parts of the world, because this boundary clay is found in many parts of the world, we find tiny grains of sand. Now, these grains of sand are composed of a mineral which we call quartz. Now, there's nothing very strange about finding quartz in sedimentary rock such as this. Indeed, many rocks are made completely of that sort of mineral. And if we look at the sort of quartz grain which might be absolutely typical of that sort, there are a few bits of blobs and so forth, but otherwise there's no particular structure in that piece of quartz. That's a tiny grain of quartz. We're looking at that underneath a microscope. That's exactly what you'd expect to find. However, if you look at the little grains of quartz which have come from these famous boundary clays 65 million years ago, you see a very different structure indeed. Now let me just adjust this because this may need a tiny bit. Hang on. Got it. Excellent, fine. Now we are going to look at a grain, a whole set of striations running across it. In fact, can you see there's a direction there and there is a direction there. These striations are most peculiar. You just wouldn't expect to see them in normal circumstances. Now, although this sort of quartz with these striations is unusual, it is found in a few other places in very, very special circumstances. And first of all, what we're going to look at here, this is an area of the Earth's surface. Now something's happening, it's rising up, and suddenly you see something's moving outwards. Now, I think we'd like to see that again. Now, what's happening here? This, in fact, is an underground nuclear explosion. Up goes the Earth. Do you see the shock wave going outwards like that? As that shock wave travels outwards, it is deforming the minerals in the crust extremely rapidly. And that's not the only place where you find a certain sort of quartz with these lineations. This is a meteorite crater. This one is actually in Arizona in the United States. If you collect the quartz from this area, it shows exactly the same characteristic striations in each tiny grain of quartz. So already I'm sure you can see where the argument might be leading. This quartz is found with the striations where there is an underground nuclear explosion, intense shock wave, and it's also found where unequivocally a meteorite has slammed into the ground. Once again, an intense shock wave has gone through the Earth's crust. And what we find, therefore, in the boundary clay is basically due to the same process. What we find there is something which we now call shocked quartz, because the deformation is so rapid and so intense that the crystal lattice, the molecules are distorted in a very characteristic fashion so that you have those lines imposed on it. That is a dead giveaway for something big and nasty. Well, the story gets more and more interesting. Again, this is one of the delights of doing this sort of work. You think you solved something, and hey presto, it turns out to be even more interesting than we realized. Here is a map of the world, as you can see. I imagine you're familiar with it. Let me orientate you. North America and South America, Asia and Africa, Australia, and its long, rather peculiar-shaped object is, of course, part of Antarctica. This is the present-day world, at least in outline. I assume that you all know about the process called plate tectonics, which is responsible for moving the continents around the surface of the Earth, so that as the millions of years pass, the configuration of the continents changes in all sorts of ways. And what effectively I'm going to do now is to run time backwards 65 million years until we find what happens. Now, first of all, there was a sort of Atlantic Ocean, but Africa and South America were very much closer together. There wasn't really any North Atlantic at all at that time. Asia, Europe, and North America were effectively still all joined together. India. What's India doing here? You belong down there. India, at that time, was in the middle of the Indian Ocean. Australia, come on, down you go. Back we go, that's right. Australia, at that time, was much closer to Antarctica. Now we are looking at the world as it was 65 million years ago. And we want to explore this story of the distribution of the shocked quartz. What do we actually see? Well, imagine this is some of our shocked quartz. Where do we find it? The story unfolds. We find it in North America. We find it around in Mexico. That's okay, there's plenty there. But we also find it in Italy, and we find it in Denmark. That's where the sample I showed you, which I collected, came from, as it so happens, near Copenhagen. And we find it even as far away as New Zealand. So we're now discovering that this shocked quartz has got effectively a global distribution. It occurs almost everywhere. But there's a further thing which we need to consider. And that is that the size of these grains of shocked quartz are not constant. In some parts of the world they're very small, but in other parts they're much larger. And where are they much larger? They are much larger, especially around North America and around the Caribbean here. Now, again, if you think about that, it makes perfectly good sense. In terms of, if you are blasting a lot of fine grains into the sky, those which are somewhat bigger will be somewhat heavier, and they will fall back to the ground more quickly than the finer grains, which might be sent round almost half the planet, for goodness sake. And that is very important, because it suggests that the area where the site of the impact was must be somewhere in this sort of area. Well, that's still a very, very big area. But again, test, 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 1 clue, 2 clue, 3 clue. We're always looking to find new evidence. Because about 2/3 of our planet is composed of water, there is naturally enough a higher probability that the meteorite will fall into the ocean, and the crater would then subsequently, after everything's died down, mind you, be covered with water. Is that possible here? Well, it is not, and we can show that with remarkable simplicity, because this is, of course, a rock, and this is a piece of basalt. Now, the point about basalt is that that is a typical rock which occurs underneath most of the oceans. That's what the ocean floor, somewhat deeper down beneath the sediments, that is what the ocean floor is actually composed of. But the basalt does not contain any quartz at all. Therefore, you cannot generate shocked quartz from hitting basalt. It won't work. Therefore, the meteorite must have landed somewhere on some sort of continent or land. And of course, that makes good sense, because when we look at the sorts of rocks which we find underneath the land and the continents, it is one which is broadly a granite, which is rich in quartz. So that shocked quartz came from this sort of rock. Now, that doesn't mean that it was actually dry land. It may well have been shallow sea. But it does suggest that our search must concentrate not in some deep ocean, but more particularly in an area which had this sort of rock underneath it. So that, again, is a crucial point. There is one final piece of evidence which matters very much again. This is one of these pieces of boundary clay. It's from the same locality in Denmark. It's actually very, very thin. This effectively is the fallout layer. But if you go to the area where the large shocked quartz grains are, the bigger ones are, the boundary clay is not about that thick. It's not about that thick. It can be up to that thick, a metre or more. Again, just think about it. A huge rock falls out of the sky, boom, like that. Up goes all this rubble into the sky and all falls down. Well, most of it is going to fall down rather quickly, close to the crater. So you would expect the thick boundary clay to be in this area. It agrees with the shock quartz, and thinner boundary clay to be elsewhere. Well, it's really slightly ridiculous, because the calculations are that Alvarez and his team estimated that there was an asteroid of about 10 kilometers diameter. And the physicists will tell us that that leads to a crater which should be perhaps 200 kilometers across. Yet I've just told you, and I hope shown you, more importantly, demonstrated, that the crater has to be on the continent. How on earth can you lose a crater 200 kilometers across? Well, the curious fact is the crater was never actually lost. It was discovered in the 1950s, a few years after, in fact, I was born, but they didn't recognize it. In Mexico, as with so many countries, there is a search, in particular, for oil. And what we have here is one of the typical oil rigs, and they're going to drill a hole deep into the ground to search for this valuable substance. And they were searching in many parts of Mexico, and they were drilling down, and they came across some rocks which appeared to be molten. Of course, they were solid now, but had been completely molten, and other bits and pieces which had evidently been chunks of rock which had come up and fallen down again. And the area where they were looking was in fact over here. This is in the Yucatan Peninsula in Mexico. And as they were drilling in, they were keeping in touch with various people, and they said, "Boss, we've just hit a whole lot of volcanic rock." And of course, back at base, they said, "Stop drilling at once, because everybody knows it's a complete and utter waste of time to search for oil in volcanoes. It's a waste of money." So they stopped, and everybody forgot about it. Until, of course, that is, the search for the crater began again. Now, this is actually a remarkably precious specimen, because it is a piece from that borehole made by the Mexican petroleum geologists, which they had interpreted as a piece of volcanic rock. But it's nothing of the sort. It is, of course, from the crater. What they thought was volcanic debris is, in fact, those chunks of rock which went high up into the sky and fell down almost straight away. And you'll also find bits of shocked quartz and the like in this particular sort of rock. So this is really beginning to clinch the argument. We actually have the objective evidence from a couple of kilometers beneath the surface of the Earth. Well, the story, of course, hasn't stopped there. The investigations continue all the time. And in particular, there is a very clever way of detecting hidden material. Because what happened is that this huge crater was formed by the giant impact, and it was at first, of course, really like a gigantic bowl. And then more and more sediments poured in till eventually the crater was hidden from human view. That's why it's so difficult to find. But more importantly, the sediments which poured into the newly formed crater over the millions of years which followed were much lighter than the ones around the edge of the crater. And what this diagram shows here is that by using special instruments which are very, very sensitive to minute changes in the gravitational field, they are able to detect the crater itself, because the blue colors are especially light areas, and the surrounding yellows and reds define the area away from the crater. It's almost impossible on a human scale to explain the sheer amount of energy. Although this body is only 10 kilometers across, the amount of energy which is actually being released in this is absolutely phenomenal. It's colossal. And the calculations suggest that if you divide the whole of the Earth up into single square kilometers, the total energy coming in that one body was equivalent to an atomic bomb going off above every square kilometer. That is the amount of energy which was let into the Earth, but of course not immediately across the whole Earth into that one area in Mexico, in the Yucatan Peninsula. So I think that the evidence for this impact, shocked quartz, iridium, everything else, is overwhelmingly strong. Is it possible that this giant meteorite impact actually was responsible for the death of these wonderful animals, the dinosaurs, and simultaneously also for the death of these glorious creatures here, the ammonites, which are a group of invertebrates? Is it actually reasonable? Well, I think we can now establish that beyond reasonable doubt. Here is, of course, a globe of the world, and I've marked here in red the actual impact site. Of course, the geography is different from today. Not radically different, but it's still different. Despite the fact that relative to the Earth, the asteroid would have been smaller than a pinhead, as I've already mentioned, the energy which came out of this thing was astonishingly high. To start with, there would be tidal waves, kilometers high, which would spread out along all the seaways, and they would go around the entire globe in about 27 hours, and they would flood all the coastal areas. Can you imagine a kilometer high wave crashing over southern England? It doesn't bear thinking about, but that is what happened. And the problems didn't stop there. Oh no. When that meteorite hits the Earth, it literally explodes, and in a way similar to, it's not the same, of course, it's not a thermonuclear reaction, but similar to, you get a fireball. Now that fireball would have been visible across an area which is roughly covered by my hand. Anything visible to that fireball would have felt intense radiant heat, and at least close to the impact, and probably for thousands of kilometers around, the forests would have spontaneously ignited. Never mind what happened to the animals. It was a total catastrophe in this particular area. But not only was there soot ascending into the atmosphere, there was of course also huge quantities of rock dust. And that explains why we find the shock quartz and the boundary clay so widely. Because within a few days, a pall of dust, smoke and rubble, fine pieces of rock, had spread across the entire surface of the Earth, high up in the atmosphere, the finer material. The sun dimmed, it literally went dark as night, the temperatures plummeted, and the mass extinction was well underway. The lights had been turned off, photosynthesis was no longer possible, the plants were dying. This was a dreadful time. So it is no fun at all. But it's even worse. This is a rock. It's actually a piece of a rock known as anhydrite. Now, anhydrite is made of calcium sulfate. It just so happens that this area of what is now Mexico is very rich in this particular rock. And in effect, the difficulty is, for the dinosaurs, that is, and the other animals, that it vaporizes very easily if it's hit by something as big as a 10-kilometer asteroid. And that leads to the ascent of huge quantities of sulfur, because this is made of calcium sulfate. So calcium sulfate then goes in to produce the sulfur. Now, we've prepared a small demonstration for you, and what Ilya is going to do is take this thing, thank you very much, and he is going to ignite this sulfur here. So I'll just let this part of the experiment proceed. Thank you, Ilya. The sulfur is now well alight. As you can see, huge quantities of noxious fumes are being produced, which include sulfur dioxide and various other nasty sorts of things. That sulfur dioxide, that sulfur trioxide, then combines with water, and what does it form? It forms sulfuric acid. It forms billions of tons of sulfuric acid up in the atmosphere because the target site included this rock rich in sulfate. The sulfur goes up into the atmosphere, is converted into this dreadful fumes here, and then combines with the water. That's our sulfuric acid. And as many will be aware, we put some of this onto the sort of rock which was very abundant at that time, at the time the dinosaurs flourished. As you can see, this is an acid rain, which was far beyond any of our petty concerns with acid rain. Huge quantities of acid fell out of the atmosphere in the rain in the succeeding years. And here we have a very, very unhappy plant. Yep. So it's the dinosaurs and the ammonites and the plants. All of them are going through this terrible mass extinction. And I don't want to harrow you, but here we have a reconstruction of perhaps what that post-catastrophe world looked like. There's one little dinosaur wandering around. Hello? Hello? Anybody there? Hello? Probably not all the dinosaurs went extinct exactly with the meteorite. It's quite likely that populations survived, especially in places away from what is now Mexico. But it's quite clear that they did not survive for any great length of time, because we don't have any today. In fact, it's clear from the fossil record that they must have disappeared really rather quickly. Now then, we have a devastated landscape like this, and we know, for instance, from volcanic islands which are blasted to pieces, that they can recover quite quickly. But we're not talking about one island, we're talking about the best part of the planet. It was 1 million years before the planet came back to full health. And we can show that again from the fossil record, and we can show it by looking not this time at the dinosaurs, but looking at the oceans. Now then, what I have got here is a Cretaceous ocean. I want you to imagine it's full of water. Okay, splash, 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 like that. Why has this man put ping pong balls in here? I will tell you. Because in the ocean there is a substantial amount of carbon. That carbon, of course, is used for building our bodies and all other organisms as well. Now, it so turns out that there are in fact two sorts of carbon. There is a heavier sort of carbon, which I'm indicating here with the red ball, and there's a lighter sort of carbon which is going up here. And these are known as isotopes. So that in the ocean we have the water and we also have the carbon, which occurs as these two isotopes. And of course we have special instruments which can measure the relative number of the light blue against the heavy red. That's the principle in any case. Now then, at this stage I would very much appreciate the help of a couple of volunteers. Oh gosh, there's a real enthusiasm today. Let me see now. Yes, perhaps use the chap here. Yes, I'd like your help, please. And we need one other. Maybe, yes, the girl who's looking very keen with the white shirt, the white T-shirt. Come on down, please. Now, if you can just stay there for a minute. Mind your steps as you come. Right. And if you come round here. Now, the first thing, just for courtesy's sake, is can I ask your name? Rachel. You're Rachel? Fergal. Fergal. Excellent. How do you do both? Now then, we are lacking one thing in this particular ocean. It hasn't got any life in it. And in front of us we've got a whole set of balloons. And could you first of all just transfer these balloons into the ocean? That's great. Thank you. All done? Thank you very much. Right, okay, we're ready. Now, what are these balloons here? These are algae, and within them you can see that of course they have the carbon. They have to. All living forms have carbon. These algae are photosynthetic, that is, they are taking the water and the carbon dioxide to make their bodies. Okay, you're familiar with all this? However, when they photosynthesize, they use more of the light blue than the red. They use more of the light carbon than the heavy carbon. And there's a very specific reason to do with the way in which photosynthesis works. So here we have all these algae. And now what I'd like you both to do is to take one of these, and don't do anything until I say so. Okay, I want you to engage in a mass extinction. Off you go. Your turn, Fergal, quickly. Excellent. Some of them are a little bit resistant. Yes, they die hard. Right, now just... Oh, you're being vicious. Let me take away those instruments. Thank you very much. Now I need to do one other thing, if you'll be so kind. Can we just remove the corpses? No, the ones which are still in here, don't worry about those, but these bits and pieces, can we just take them out? Can't stand this sort of thing. There we go. Ugh. And we'll put them in the bins there. That's terrific. Okay. These are ones which are moribund, okay? And we do have, of course, a survivor. Remember, if there was a mass extinction which was so terrible to wipe out all life, then certainly we wouldn't be here to talk about it. So a few things have got to pull through. Now, I don't know if you look closely at the relative numbers of the red and the blue balls beforehand, but Rachel, can I ask you, just in your opinion, do you think the ratio has changed here now that we've burst all these balloons and remembering how the algae actually behave? What do you observe?
There were more red before. Right?
Absolutely, right, and now there are more...
Blue.
Rachel, you're right. Yes, there are more blue than there are red. The ratio between the heavy and the light carbon has changed because nearly all the algae have died. So, at this stage I need to explain this in a bit more detail, but first, Rachel and Fergal, could I thank you both very much for your assistance. Many thanks. Thanks a lot. The story actually is that we can measure that isotopic ratio quite simply using special instruments. And when we do that, and when we look through the record of this, we see in fact that it fluctuates slightly, but then suddenly at this point there is a massive fluctuation which is equivalent to all those blue balls joining the system. And that is exactly coincident with the iridium anomaly. So there's a correspondence here. This is when the oceans die. But the really important thing is that then the carbon takes, or the curve for the carbon, takes the best part of 1 million years to get back to health. And that's why we deduce this immense period of time before things recover. Now, in this end Cretaceous extinction, we estimate that something like 70% of all the species on the planet went extinct. It's a rough estimate. That means, of course, that not everything did go extinct. There were, of course, survivors. And as we are, in a sense, products of that time of trauma, in other words, we must be part of those survivors, otherwise we wouldn't be here, then we want to investigate who came through. Now, I hope very shortly that we will be able to see one of these survivors. Hello, this is Colin Howard, and as you can see in his hand, he's got a magnificent snake. Colin, could you please tell me what sort of snake this is?
This is a Burmese python.
Okay, and how old do you think this is, or do you actually know?
It's approximately 4 years old.
Right, okay, well, that sort of thing. And this is an example of one... Sorry, just a lovely animal, absolutely glorious. This is one of the examples of the survivors from that disaster, because, of course, this is the age of snakes. The snakes are very, very important today. When did you last feed this snake, Colin?
This was fed about a month ago.
Right, now having just seen what has come in, I think we might thank Colin very much indeed. So may I thank you indeed for your help. Many thanks indeed. Thank you. Snakes are survivors in as much as the world is full of snakes. It is the age of snakes, but it's not only the age of snakes, it's also, of course, self-evidently the age of mammals. The important observation about the mammals, to which of course we belong, is that at the time of the dinosaurs, most of the mammals were about the size of these little Russian hamsters, or only slightly bigger. But now, of course, we have ponies and antelopes and giraffes and camels and whales, all of which came from things similar to that. And in the next lecture, in fact, I'll tell you a little bit more about how some of that occurred. So it's also the age of mammals. But, in addition, let me lift these two lovely creatures very carefully indeed. It's also the age of birds. Birds are very common both in terms of individuals and also species. They attract our admiration, they have lovely plumage, they sing often beautifully, they have complex social systems, they are very interesting creatures. And once the air, when the dinosaurs were around, was cleared of the flying reptiles, the pterodactyls and things, then the birds were really in a position to take over. The point about all these cases of the age of snakes, the age of mammals, and the age of birds is that there were, if you like, vacancies. That is, that the world had been dominated by the giant dinosaurs. It had been dominated in the air by the pterodactyls and the other flying reptiles. In the oceans, it had been dominated by these huge marine reptiles. All of those went extinct. And one of the most fascinating things you can learn about the history of life is how new opportunities are seized by the survivors. Now, I could give you umpteen examples of what actually happened, but I thought I couldn't resist, frankly, because I think this is one of the most spectacular of them all. I've just shown you some living birds, beautiful creatures, and this is the skull of a turkey. And this is the skull of another bird. It's a real skull. It's not enlarged. This is its size as it was. It lived in South America about 15 million years ago. It's now extinct, perhaps just as well, because you can see this sharp stabbing structure here. It's so large that it was in fact flightless. It ran around on two huge legs. It was a bit like a gigantic killing ostrich, and it hunted small little things about this size, mammals in particular. Very fond of mammals it was. And that is just one example about what happens if you remove one group of predators and then allow another group to radiate, as we say, that is to expand into their position. In the last 500 million years, there have been 5 mass extinctions. We are now in the 6th mass extinction. That 6th mass extinction is not because of meteorites, self-evidently. There's no crashing through the roof, we hope. Nor is it due to ice ages or the various other things which have been proposed as mechanisms for mass extinction. This mass extinction is due to us, you and me. The world's population is increasing at an incredible rate. The degradation of our environment and the pollution are leading to inevitable severe species losses. Most of those species you'll never know about. There'll be little things like worms and beetles, but some of these species will be, of course, very familiar to you. They are, of course, such famous examples as the wonderful Indian tiger. Who wants to see this go? What a creature. Marvellous. And then, of course, in the oceans, we have the fabulous whales. And in the next lecture, I'll tell you a little bit about how the whales evolved from land-going animals. And so it is that in the next lecture, I would like to tell you a little bit more about how invasions, how novelty, how the motor of evolution ends up with a planet which is so beautiful and which we are so very, very lucky to live in. Thank you very much. If you would like a booklet or a video pack of all the lectures, which includes a free booklet, please send a cheque payable to BBC Education to BBC Education, P.O. Box 5620, Newbury, RG14 2YA. The booklet is £4.50, the video pack is £29.